In this video, we'll be solving this problem 3 and problem 4. Okay. And before we start with their solution, let's look at something here. Say we are given a number a multiplied by b is equals to m. Suppose this is Diophantine equation like we were having before. Instead of this, we were having something like x plus 2 x plus 3 is 21, something like this. So here just a is x plus 2, b is x plus 3, and m is 21. Instead of 21, let's take it to be 12. Okay. Now, as I've told you before, that knowing their GCD can be very useful. And why is that? Let's see. If we were to solve this equation, what we would do is we will take cases, all possible cases, which were 1, 12, 12, 1, 2, 6, 6, 2, 3, 4, 4, 3. Yeah, these are the all possible cases that we'll be having. Instead of taking x here, let's take it to be y. Okay, so if we didn't know what these two terms GCD were, we'd then have to look at all these cases separately. All these will be solutions 1, 2, 3, 4, 5, 6. But if somehow we can find out that their GCD is 1, then immediately we can discard these two options as their GCD is 2. So then we'll only have to look at these 4 cases. Okay. Had we known, or if we had somehow figured out that their GCD is 1. If in some case GCD is not turning out to be 1, that's also fine. Even better in some cases, suppose their GCD was coming out to be 2. Yeah, say their GCD was coming out to be 2. Then this case will be discarded because their GCD is 1. These two cases will also be discarded as their GCD is 1. Then we'll only have to deal with these two cases. So in the first problem, first case when the GCD was 1, we'd have 4 cases, and in the second case when the GCD was coming out to be 2, we'd only have 2 cases, and their GCD cannot be other than 1 or 2 here, as if it was 3, there is no solution then. Okay, this is how knowing GCD can be of immense use. And instead of writing all these possible cases, then discarding cases, that's not what we will be doing. What we will be doing is, say we have figured out that their GCD is 2. Then 2 will divide x plus 2 and 2 will divide y plus 3. So we can write x plus 2 as 2m and y plus 3 as 2n. And since the greatest common divisor between x plus 2 and y plus 3 is 2, these two numbers have to be co-prime. Because if they had something in common, then it will contribute to their GCD. Then their GCD won't be just 2. It will be something greater than 2. So these two numbers have to be co-prime. Okay. So this equation then becomes x plus 2 y plus 3 equals to 12 will become 2m multiplied by 2n equals to 12. This will then become m into n equals to 3. And we know that GCD of m and n is 1. We'll only have these 2 cases. So this is what we'll be doing instead of writing all the possible cases and then discarding them. Okay, this is what we'll be doing. Let's take one more example. Here, say I have x square plus x plus 1 square minus x plus 1 with 36. Now suppose their GCD was 3. It's not that their GCD is 3, I'm just telling you it's not right. GCD could not be 3. It could turn out that GCD is 4 to whatever. this is not correct. I'm just telling you, say if it was, because it will take time for me to find out examples whose GCD is 3. So we'll just take this one as for our case. Suppose their GCD was 3, so then we can write this term as x square plus x plus 1 as 3m, and this can be written as x square minus x plus 1 as 3m, where m and a GCD is 1. So this equation then becomes 3m multiplied by 3n equals to 36. This then becomes n into n equals to 4. Now we know their GCD is 1, so this case cannot be there, as the GCD is 2 in this case. So the only possible cases we'll have is 1, 4, 4. And we can then put back the values of m and n here, and we can find out our values of x. And now if we had something like, say, something like this, say a into b is m square, where a here is again that big expression, some big expression, in b also is some big expression, and m is just a number. Okay, suppose GCD of a and b was 1. It is given to us, GCD is 1. Now look at this. Let's look at the prime decomposition of m. M can be written as 1 L1 P1 L1 P2 L2 Pn Ln, and since it is raised to the power 2, we'll hide 2 here everywhere. Now since GCD of a and b is 1, they cannot have any prime in common. It cannot be like that P2 will divide a and P2 will also divide b. This cannot happen. So a will have certain many primes and it will have all its powers, and b will have certain many primes and all their powers. So we can say that, say we had pi 2li here and pi plus 1 2li plus 1 was here. So we can say a can be written as, say a was getting these many primes, these first I primes, and b was next whatever rest of the primes were left, those many primes. So a can be then p1 2l1 p2 2l2 pi 2li, and b will then be pi plus 1 2li plus 1 dash pn 2ln. And now we can take this power 2 outside, or maybe like this, p1 l1 dash pi li, this were 2, and this is nothing but some number. We don't know what it is, but it is some number. Let's take it to be x to the power square, and this similarly will turn out to be some number which we will say y to the power square. So what we are getting here is, if the GCD is 1, these two will also be squares, perfect squares. So what we are getting is a will be x square and b will be y square, where GCD of x and y is 1. You can see there is no common prime, and there cannot be no common prime, as GCD of a and b is 1, so GCD of x and y has to be 1. So similarly, if we had, say, a into b m cube, and GCD of a and b was given to us 1, so we can from here say a will be x cube and b will be y cube for some integer x and y, and m will be equal to xy. Similarly, if we were given a b equals to p to the power n, we can then say a is x to the power n and b is y to the power n. We were given a b GCD is 1. Then only we can say this. if we are not given the GCD 1 or some other GCD, I'll take the case when the GCD 2 or 3. In only those cases we can do this. That P is XY. Now say the GCD was not 1, the GCD was something else. Sorry, this P is not prime. Let's take it to be some integer M. Okay, now let's take the case when the GCD is not 1. AB equals to M square, where the GCD is, say, 5. Could be anything, I'm just taking it to be 5 for now. So then we can write A as 5M. Let's take it M here, let's take X. 5X. Let's also not take X, let's take some other number. A is 5. Let's take L1. And B is 5 L2. And GCD of L1, L2 is 1. So this can be written as 5 L1, 5 L2, M square. This is 25 L1, L2, M square. And L1, L2 equals to M upon 5 whole square. These two are integers, so this has to be integers. So M divided by 5 will be some other integer. Let's call it M1. So we have this. L1, L2 is this. And since we know L1, L2 GCD is 1, this equation then again reduces to a previous form. So from here we can say L1 is x1 square and L2 is y square, and M1 is equals to x and y. So this is what benefit we'll have if we know just the GCD of A and B. And in questions you will not be getting A and B. You will have these big expressions as we have seen before. This equals to some number 21 or 36 or whatever. These have like big complicated expressions. Z 3x 2x plus 4y square plus z. Some of these big expressions, and if we can find the GCD is fine. You can see how useful it can be. If we cannot find GCD, then we'll look for some other way. There are always some other way. Okay, so with this information we are ready to look at our problem number 3 and 4. Here we are also given that x, y and p are odd. It is given to you in the problem. So let's look at its solution. Now the identity which we have seen in previous videos, using that we can factorize this. The identity was a4 plus 4b4 can be factorized into a square plus 2ab plus 2b square, and a square minus 2ab into b square. Here b is 1, so using this identity we can factorize, it will be factorized to this. Okay, this is 4. Now we try to find what is their GCD, and to find their GCD, let's see how we can do that. Say its GCD is D. It can be anything. For the moment we are saying it's D. Let's see what properties will D have then. Since D is their GCD, D will divide x square plus 2x plus 2, and D will also divide x square minus 2x plus 2. Now since D divides this term and D divides this term, so D will divide their subtraction as we have seen before. So D will divide 4x. Now also look at this. Since D divides these two terms, D divides these two terms, so D then will also have to divide this term. but we know that p and y are odd. It is given to us, so d divides some odd number. So can d be even here? Can say a even number, say 6, can it ever divide an odd number? It can never. An even number can only divide an even number. So d cannot be even. D has to be odd. So from here we get d is odd. We can write it here, since d divides p y to the power 4, therefore d is odd. Now since d is odd, d then we can write as d comma 4 as 1, since 4 is even. Now using what we have, using the property which I've seen in a previous video, which was that if m divides a and b, a multiplied by b, and GCD of m and a is 1, then m will divide b. This we have seen before. So using this we can say d divides x. Okay, now since d divides x and d divides this whole term, so then since d divides x, d will also divide x square, and d will also divide 2x. So then d will divide their addition. D will then divide x square plus 2x, and d then also will divide subtraction, this term and this term subtraction. So d will then divide, if we subtract these two, we'll get let's write it quickly here, minus x square minus 2x. From here we get d divides 2. But since d is odd, from here we see d has only two options. D can be 1 or d can be 2. But since d is odd, this case is discarded. D is 1. So from this we can say that GCD of these two terms is 1 after all this calculation. Okay, so now how will this be useful to us? You'll see. Okay, let me rub it real quick. Now that we have shown that their GCD is 1, we can write it here, x square plus 2x plus 2 comma x square minus 2x plus 2, its GCD is 1. So now we can say that these two is equals to y to the y raised to the power 4, and p is also there. For the moment, let's forget about p. Let's forget if p was here. So then we can say this term can be m square. So we took x, so x is already here, we have to take some other variable. So let's take l. So this is l square, l1 square, and this is l2 square, where y is l1, l2. Let's write it again here. But since our p is also here, what we can do is, one case would be p comes in the in its prime decomposition, so p can be here, and in other case p can be here. So these two are the only cases that we'll have. So what can we do from this? Let's write it as, we have now x square minus 2x plus 2 is coming out to be L2 square, and x square plus 2x plus 2 is coming out to be PL1 square. So from here we can write this as x minus 1 whole square plus 1 equals to L2 square. So what this is saying is, we add 1 to a whole square, we get another whole square. This never happens except we add 1 to 0. 0 is a whole square. If we add 1 to 0, we get another whole square. Except this case, we never get another whole square. Add 1 to 4, you'll get 5. You'll never get another whole square. So for this equation to be true, this term has to be 0. So x has to be 1. So if x is 1, then we have this term will become 5. This PL1 square will become 5. And x is 1, we get L2 is L2 square is 1, so L2 is plus minus 1. And from here we get P L1 square is 5. But since P is prime greater than 1, of course, so P has to be 5 and L1 square has to be 1, which then gives us L1 is plus minus 1. So the solution that we are getting is, we got x is 1 and we got P is 5 and we got y as y can be 1 or minus 1. From a case 1, this was case 1, we got the solution. And with our case 2, you will have something similar. You will have P as 5, x as maybe plus minus 1 and y as 1, something like this. So all solutions you'll have is, all the combination of these, you'll always have P is 5 and xy will come out to be 1 1 minus 1 1 minus 1 minus 1 and 1 minus 1. These are the all solutions that you'll be getting. This completes our solution. So let's quickly see what we did here. First we factorized it using our famous identity, and then we tried seeing if we can find the GCD. As a matter of fact, we did. The GCD did turn out to be 1, and using what I told you in the beginning of the lesson, we got these two cases. We dealt with case 1 here. Case 1 gave us these solutions, and case 2 similarly will give you these solutions, and from that we have these are our total solutions or all solutions.